always look forward to Megalithomania. It's where I get my feel of strangeness and wonder of the ancient world, and it strikes me as a quite unique event. Here we've got worlds crossing. We've got the alternative and the academic. We've got the visionary and the scientific. And I suppose that's no surprise really, because the sites themselves encompass both this scientific and this visionary side. And we have these crossings between worlds, crossings between man and the cosmos, between imagination and engineering, between symbolic and actual, between myth and history. Now, wherever you've got a crossroads in the ancient world, you have Hermes. Hermes, the strider of boundaries, the crosser between worlds. And Hermes is traditionally thought to have brought language and culture to the universe, or to humans. Now, the figure of Hermes is thought to derive from the word herm, meaning pile of stones left at the crossroads, perhaps as markers or as offerings. And here's a pile of stones. And we have these trickster culture bringers like Hermes or Mercury or Thoth or the coyote in every culture. And let's look at Thoth. This is from Luxor. And something that's always strikes me about Thoth is this beak, this ibis precision beak he's got. And you think about how sharp and precise that quality is. And it's precision that is very fascinating and will play a big part in this talk today about measure and about how the ancient people thought. And something that strikes me about what makes us curious, not just about these ancient sites, but to explore the wider world. And it seems to me that something that we all experience when we're in these places is the presence of intelligent detail. And that might be the intelligent detail of a pattern, or of an emotion that we feel, or of a measure or a dimension of the particular site. But it's the same sort of intelligent detail that stimulates us when we see a rock pool with this whole world inside it, or we're in a forest and our ears start to expand and hear all the thousands of sounds. And I'd argue that it's intelligent detail that really makes us who we are. It's what we search for in a building or a poem or a piece of music. And our imagination is stirred by these layers of potential discovery. And I think that's what draws us back over and over again to sites that we're talking about at events like this. And this intelligent detail is Hermes all around. The curious mind is sparked by the presence of this intelligent detail. The thing is about Hermes, sometimes he leads us, and sometimes he leads us on. He's got that trickster quality. But when we pursue these details, these offerings that Hermes gives to us, then sometimes a whole world can unpack from just a tiny, tiny thing. And this is very much the way that the ancient peoples were thinking about numbers. They've embedded all of their knowledge into very, very simple objects. And today I'm going to talk about what happens when we open up and unpack the sort of ideas that the ancients are building into not just their architecture, but the foundations of their entire culture. And we're going to look at one of the most ancient artifacts known to mankind. It's perhaps our oldest scientific instrument. It's been in use for over 8,000 years, and it hides in plain sight. It's absolutely ordinary, yet it contains the most ancient of secrets. It's eminently practical, yet it describes a visionary worldview. It's an engineering marvel and a mysterious bridge between worlds. It is the ruler. Hidden in this object, which we all ignore because it's all around us all the time, are secrets that, well, John Michell said if we want to understand how the ancients thought, we have to understand their measurements. We have to understand the standards and what they took care over. Now, there's this word precision. Precision essentially means taking care. So when we find precision, then maybe that's something we should pay attention to as researchers. Now, measure is a massive subject, and ancient measure, part of measure, is still a massive subject. So in order to cover as much as possible in an hour, we're just going to leap into some of the key features of what has come to be called ancient metrology. And here's the two figures behind this reconstruction of the ancient picture of measure. John Michell, who with his book Ancient Metrology cracked some of the key features, and John Neal then went on for many years to expand that enormously. And for those of you that haven't read his books, Ancient Metrology, Volume 1 and 2, I'd really recommend them. They're an enormous contribution to the subject, and you're really missing out if you haven't read them. But hopefully today we'll be able to dip into that and touch base with the most important points. So we've got threads to follow. We've got artifacts, we've got sites, we've got writings from the ancient world from people like Plato, and then there are threads from contemporary writers and researchers, people like René Schwald de Lubigs, Ernest Maclean, the musicologist, Hans Kaiser, the harmonicist, and Keith Critchlow, and not least John Michell and John Neal. So this is a story that really has it all. Discoveries, a secret model of the ancients, hidden artifacts, even a questionable death. There's guild secrets, ancient scientific instruments, temples and pyramids, number mystics and revolutionaries, tyrants and surveyors, and they're all dancing around a great secret of the universe, a pillar of existence, and it's all coming from that simple ruler. Let's look at number and quality. What can we really know about primordial perception, about the way the ancient people thought? There's an entire stream of thought that weaves through history like a golden thread, from the ancients to classical writers such as Plato, and onto the great figures of the Renaissance, through the Romantic poets and contemporary philosophers such as Rudolf Steiner. And this stream of thought seeks to apprehend the world through its qualities. It's been called the language of symbolic analogy. It's been called the primordial language, the doctrine of correspondences, the language of the birds. Through a direct perception of the qualities of life and being, a natural knowledge begins to grow. It's an inevitability, just like you put hands and clay and fire together, and inevitably you're going to get pottery. We're naturally attuned to this knowledge that in the end all of life has grown up upon. And this perception of quality, it reminds me of Blake's short poem about the thistle. And he's walking along and he sees this thistle, and he said, and this, I'll quote a little bit from the poem: "For double vision my eyes do see, and double vision is always with me. With my inward eye, 'tis an old man grey, with my outward, a thistle across my way." And Blake's really talking about a perception that simultaneously apprehends both the imaginative or imaginal aspects of an object or an entity and the sensory ones. It's not making a split, it's not making a duality. It's what Owen Barfield, who is a friend of Tolkien and model for Tom Bombadil, called the primordial language. And Here's one of Blake's pictures here. I didn't put the poem up because I preferred to actually see this divine geometer measuring the cosmos. Now let's talk about how we perceive quality. This is going down and down. I'll be kneeling on the floor by the end of it. Schwaller de Lubicz uses this word nita to describe quality or function. And he also makes the point that the Egyptians talked about their gods and goddesses not as gods and goddesses, but as nitas. Or he suggests that our word nature, the natures of things, are what they're talking about. And Schwaller also makes this really interesting point that these qualities, these natures, they are embodied in the physical world through gesture. We see these gestures here, how they immediately convey the emotion, the intention, just with this simple, pure expression. We could see this as a gesture. But do we see this as a gesture too? Or this? And through these gestures, we're able to perceive these qualities that are unperceivable and invisible, but that are contained in everything. And when we think about what the foremost of these qualities are, Christine quoted from me earlier, and I'm going to talk about the same sort of thing again, is those foremost of qualities are number. Number itself is permanent. It never changes. It's the one constant in a universe that is, or in a cosmos, that is temporal, that is bound to time. Even a mountain or a sea will eventually shift and change, but number itself was here first. It was here before the cosmos came into being, and you could say that, you know, the cosmos dreamt itself into being through number. And, you know, every form of life and consciousness on the planet, from viruses to galactic superclusters, bigger than this planet, grows on this substrate of number. And these unchanging causal properties, they didn't escape the attention of early humans. They universally accorded these permanent forms with divine status and wove their patterns into the very fabric of human society. Since deep antiquity, the study of number in its guises has furnished humanity with a science that is both inner and outer, symbol and tool. And all phenomena we can examine or encounter in the physical world, they're subject to these qualities. Now, traditionally, the qualities of number have been studied through number itself. These are the timetable blocks up there. Then below we've got a ruler. Now, you'd think the ruler would play a part in geometry, but actually, as we're going to see, that the ruler's far more connected to music and harmonics. In many ways, it joins music and geometry together. And here we've got the protractor and the clock. These four artifacts that symbolize our long-going and ancient relationship with the number arts, arithmetic, geometry, harmony, harmonics, and astronomy. The Sanskrit word svar means light, and there's another word svara meaning sound. And this really equates what was being thought when these terms were being conceived, is that number itself, because we know sound is an expression of number. We tend to, as humans, think of number as this is mathematics, and that we've all had, to varying degrees, quite a brutal education in mathematics. But the universe doesn't distinguish between sound and geometry and pure number. It's all happening all at once. And so when the Vedics were talking about sound and light as a similar property, they're also talking about number as a similar property. And so we could say that numbers themselves are luminous. Here's some of these are early pictures of these number arts. So we've got arithmetic in the top corner, top left, and geometry in the top right, and that's astronomy. And below this engraving is harmonics. And you see that little thing, this guy with the big sleeves playing with. Oh, I've got a pointer here. This here. This is known as a monochord. And this is just a single string stretched across a sound box with movable bridges. You think of the frets on a guitar, how they're able to, they're all fixed, but the monochord, you can put them wherever you want to make whatever note you're actually looking for. Let's not do that just yet. And these approaches to number have always been seen as quite connected. Definitely they're all interpreting the same thing, but as discrete subjects, as subjects that have analogies to each other but can't be directly mapped onto each other. And we're hopefully going to see a slightly different picture of that today. We've got, going backwards and forwards here. So we're looking at geometry, and we see particularly famous examples of proportions in geometry. This is the golden section. This little symbol here known as phi. When I talk about, I'm going to talk a little bit about the golden section. I'll probably just slip into talking about phi. So when you hear me say phi, I'm talking about the golden section. Other relationships, and these are all known as irrational relationships. That means that you're never quite able to express in number the relationship between 1 and the golden section. You're never quite able to express the relationship between the edge of the square and its diagonal. In mathematics, these numbers go on infinitely, like pi. You can't quite get to the end of it. The number itself is not quite expressible. Now, this wasn't really suitable for the ancient mind. They considered the physical world, the cosmos, to be completely understandable, that it had been that it literally was a gift from the divine. Henri Corbin, the perennialist, talks about the forms of the world expressing or being epiphanies of the qualities of the divine. And we can take this definitely into the number arts as well. So here we've got a string. If we imagine this 1-1 as a note, now if we double that string length, we suddenly have the same note but an octave lower. If we half that string length, again we get the same note but an octave higher. And so we're starting to see, well, this is going lower and lower here. Here's some more intervals. So these are different. If you see 3/2, we're just dividing that 1 in half and adding another half. So we've got 3 halves. 4/3, dividing that 1 in 3, adding another third. And we can continue this process over and over again to develop what are called generally the Pythagorean intervals or Pythagorean tuning. And in music, we don't tend to use this scale as much now. We've stretched all our octaves so it all fits equally, so we can have music like jazz and move backwards and forwards. But for the ancients, music was based on these pure number forms. And here's these same intervals, and it shows that these pure number forms actually emerge in the vibration of the string. And not only that, but we even have tiny little hairs within our inner ear and shapes within the cochlea that reflect these lengths and reflect these intervals, and it will light up certain nerves only when those hairs are hit by this tone. And Plato developed this thinking about music as number as a whole creation myth. His dialogue Timaeus describes the creation of the universe through these 2 rings that he puts together and makes into an X. So if you imagine 2 circles, and you put them together and you see them from the side and you've got an X. And from these 2 circles, which Plato calls the different and the same, the whole of musical creation in his model emerges. So here we've got on the left where it says times 2 at the bottom, that's what Plato would call the sameness. So, sorry, the difference. So on the left is the difference, and on the right times 3 is the sameness. And so he's saying that the same intervals occur, the same notes, if we look at these same intervals, they occur in different octaves. So on the right, where it's times, on the left, where it's times 2, we're looking at this doubling principle, this octave principle. And on times 3, we're looking at triples. Now, Ernest Maclean made a very interesting point that because Plato's talking about an x, he's actually talking about the numbers going both ways. And if we see on this right-hand diagram, we've got everything going up being divided by 2 on the right and 3 on the left, and everything going down being multiplied by 2 on the left and 3 on the right. And Maclean equated this with what he called Shiva's drum, and he's very convinced that that's present in the Vedic culture. And so Plato has formulated, and it must be part of an ancient model, he's formulated this image of the cosmos as music, as harmonics. This tool doesn't have to be just used for these simple harmonics. You know, we can take this central diagram here is exactly the same as this one at the top, except instead of making 1 our center, we've made 2, 1, 6 our center. And still, it's dividing, going up, and multiplying, going down. We don't even have to use 2 and 3, we can use any numbers. It's a mathematical tool that could be applied to comparing numbers of different sorts. And so far, with Plato, he's just talking about the whole of the cosmos being generated from the numbers 2 and 3. Now, there's a slightly expanded scale of that called just intonation, which also includes the numbers 5. And you see how we've got these extra intervals, 6 over 5, 5 over 4, and how with 5 over 4, we've just divided our 1 into quarters and added a quarter. With 6 over 5, we've divided our 1 into 5 and added a fifth. And that's the principle. The Greeks called these super particulars, numbers that were different by just 1 digit between the top and the bottom. Now, Iamblichus left this tiny little footnote in some of his writing, and it looks very similar to Plato's image of the world soul that we've got here, because Plato described this musical creation as the creation of the world soul. And so we've got Iamblichus's picture here, but notice it's slightly different. Everything on the left side is the opposite of everything on the right side. So we've got 1 over 2 on the left, and we've got 2 on the right. Now, we could describe that 2 as 2 over 1. They're mirror images of each other. In mathematics, this is called a reciprocal, which literally means forwards, backwards. And what Hans Kaiser, based on the German harmonicist Albert von Thimus did, he diagrammed Iamblichus's picture here into this grid. And this on the right, this long bar, that's your monochord string. That's a single line with a soundboard underneath. And by choosing your interval, say you want to choose 3 over 2, you choose the dot that says 3 over 2, you take a line from 0, and it immediately divides that side perfectly into the right interval. Now this is pretty mind-blowing, really, is that through a regular grid of numbers, a geometrical length is able to be established. And really, this is fascinating in terms of the word harmonics, because the word harmonic means both music and measure. It's an external length, and it's an internal experience. And this must have blown the minds of ancient people to see that sound makes me feel like this, and yet I can quantify it, I can measure it in an exact amount. But this is still quite complicated. It's, you know, that's a big thing to draw every time you want to devise stuff. But there's a simpler way, because this is just a numerical expression of this diagram here. Now this diagram goes by loads of names. Most recently, Malcolm Stewart's referred to it as the star cut, which I think is a lovely name for it. But Tons Bruns called it the, well, it's been named after him as the Bruns star. We've got Kaiser calling it the harmonic division diagram, and it's even called the fairy sequence by mathematicians. So this diagram is so embedded in our thinking, in the thinking about ancient measure and about music, that it made me start to think, when I started to talk to John Neal about his work and started to understand what he was doing, that this diagram must play a part, because in the end, it's a way to divide a distance into regular measurable parts. Here's sort of how it operates. Here's the square on the left at the top, and we've got a triangle basically, just joining each corner to each centre all the way around until we get to this bottom left drawing here. And look what happens. Completely naturally, this diagram divides our space up into thirds, quarters, fifths. That in itself is very, very interesting. It's interesting that it works in any rectangle, not just a square. But you also discover, when you start to play with this diagram, that it will continue giving you a series of rational divisions. You know, I've gone down there to a sixth, my lines go to a 12th, but I could go to 1/2050th if I wanted, or if you had the stamina. And that this device is a practical method for dividing any length into equal rational amounts. Measure. Measure is so important, and you know, there's lots of factors that come into play when we start talking about measure. If you think about number in the imagination, whether that's the mathematical imagination, where circles are all perfect and triangles are all drawn with perfectly straight lines and angles, or our imagination and how we use it to interact with the world. Now, as soon as a number comes out of our imagination into the physical world, it becomes a measure, it becomes a length. And this, I find this particularly interesting, this idea of scale. Measure's always related to scales. They always create a whole series of regular divisions. In fact, measure itself is an image of the properties of number. And this idea that scale means cut. Now, when we think about this diagram here, this is doing exactly the same. It's cutting, and division itself is cutting. Now, the division has been equated with the creation of the cosmos for tens of thousands of years. And, you know, again, Henry Corbin talks about the divine literally tearing itself apart in order to come into existence. Which quite nicely he calls this the ultimate act of pathos, which I find quite nice. So now we're really going to get into it, and you know, it's well known that if you want to talk about a complex and difficult subject, that you should get people to travel from all over the country and put them in a dark room on a hot day, and yeah, after lunch, possibly a boozy lunch, getting over from a hangover yesterday, and so I'm sure it'll all work perfectly. So this is what John Neal and John Michell have discovered and proved beyond, you know, any doubt really, because, you know, if you're familiar with John Neal's work, he's got thousands of data points, thousands of measured temples, units, rulers, and this data has essentially been collected by the archaeological world. So it's non-controversial data that John Neal has used to solve this problem. And so all the traditional units of measure are all related through these simple harmonic intervals. And we've got the simple division of the body. We've got our palm, we've got our arm. Now from the elbow, the top of our fingers is a cubit. We know a foot. From our chest to the tip of our fingers is a yard. from our shoulder to the tip of our fingers is a long cubit. And this sort of leads the common perception of measure to be thought to derive from the body. We've got this story that, you know, they measured the ruler's foot, and from that we were able to, they constructed a whole system of measure. Now this is completely arse upwards. What it actually is that the body was used as a mnemonic, as a way to remember these intervals. And the feet themselves are not based on ruler's feet, they're based on mathematical principles. Here's some of the relationships between the shorter measures. Now, the foot itself was divided into 16 and made into a digit. And here we've got palms, half cubits, feet, a riemann, which is like a short cubit, long cubits, pace, yard, step, and finally furlong, although it's not final in the list, but on this list it is. The furlong is the stature of a man, the height of a person. And we've also got longer expansions of the feet. We've got cables, plethrons, stades, rides, miles, and these allow us to take these individual measures and expand them to fit the project that's being worked on. Here's an example. Now, every mile is 5,000 feet. We know the length of the English mile, 5280 feet. So we divide that by 5,000. That gives us our foot, 132 over 125. And we know that that is a foot of this times this little extra nudge. So an English mile is 5,000 Persian feet. We'll look at this extra nudge in a little while, because what we're doing is we're looking at the intervals that are everywhere in the data that John Neal studied and put together, that all around the world, the ancient measure system fits into a simple tuning system. And we saw how Plato and the Pythagorean tuning system used just the number 2 and 3, and that expanded to become the just intonation system of 2, 3, and 5. Now, the ancient measure system also adds these numbers 7 and 11 in. And any of you familiar with the common abbreviation of pi as 22 over 7 will make that connection, and that's certainly what John Neal and John Michell did. They made that connection and saw that they'd added these two extra numbers, 7 and 11, in order to be able to work with those irrational numbers, those numbers we can't reach the end of. They're looking for solutions that allow them to work simply and quickly with those numbers. And we'll see that these are both practical solutions and symbolic solutions. Here we've got a list of some of the feet from around the world, and we see these harmonic, super particular numbers. There's one or two here that aren't, but there's a reason for that. But these super particular numbers are found all over the world. Now these feet, this is the nomenclature, the naming that John Neal has assembled in his work, and it's a very useful way of doing it. He's named them after the place where they were first discovered. But just because something is, say, a Roman foot, it doesn't mean that it was only used in Rome. In fact, we'll find Roman feet in a little while going back far, far further. So these names are really just to help researchers. It allows us to think of everything all under one system, and you know, it doesn't mean that that's where they originated, because we're looking at a musical scale. We're looking at a series of notes that the composers, the architects, the designers can use in order to express their idea or express this quality of the cosmos being about number. Don't worry if this goes out of your head. It takes a while to take all this in. And now these are the lengths. It's quite hard to see, this slide hasn't come out too well. But if you can see behind, that's our star cut, our harmonic division square. And all I've done here, this is really my main contribution to the subject, because John Neal's done so much that there was almost nothing left to do. And so here we've got this square. You can just about see those yellow lines in the background, and each of these white columns is one of one of those measures here. And so geometrically, it's very easy to create these numbers, which might look long and complicated on paper, but all I've done here is added a fifth, just like we did with those intervals where we changed a fifth into 6/5. So I've just done that on the side. You put in one diagonal, and all the points are there in order to create these measures. And this is really a big breakthrough for me, being able to use this star-cut diagram to expand and reduce lengths in order to practically create these measures. Because if humans will always seek the most practical solution, they'll always use the easiest method in order to get something. We're ultimately quite lazy. So I won't do that just yet. So we've got these ancient measures, and we see a set of notes here. But something that researchers for many years have noticed is that there's variance, quite small variance, quite little nudges backwards and forwards on these measures. And that's always been presumed to be a copyist error. Now that is absolutely not the case. It's not a copyist error. What there is there's these tiny little intervals, these tiny microfractions that nudge the foot slightly longer and slightly shorter. And that allows the designers, the architects, the surveyors to fit whole numbers of units into their space. Because if we remember, the whole basis of the ancient number system, of the ancient number science, was to preserve these qualities of number. And so whole numbers of units were looked for in the dimensions of temples. And so we've got these tiny little microfractions. And what happens is that these microfractions are multiplied to make compounds in order to vary the lengths of the feet. Partly, like I was saying, in order to have whole numbers in the dimensions. But where do these fractions derive from? Now, there's dozens of ways into this subject because it's so enormous, but we're going to look at it in terms of pi and phi. Now, what is fascinating is that pi, this relationship between the diameter or radius of a circle and its circumference, and phi, the relationship of growth in so many plants and animals, and even further into the wider universe, they're locked into this dance. Now, not only have we got pi and phi here, we've got this 6 to 5. Now 6 to 5 is 1.2, which is 12 divided by 10. Now, if we think about early counting systems and how we count, obviously we're faced with number from the second we begin to exist, because here in front of us, we've got 10. But at the same time, we've got all these phalanxes, all our joints in our fingers, and we've got 12 here and 12 here, and a counter ready. So the idea that early number systems were both using 12s and 10s is found over and over again. We've got this division of the circle into 360. We've got the Babylonian use of 60s in its mathematics. So let's look at phi, and then we'll see how phi and pi work together. Now, I've been talking about 11 limit tuning. 11 limit tuning, as we saw, is just using these numbers 2, 3, 5, 7, and 11. So we've got this natural sequence of fractions and numbers that emerges from the golden section, the famous Fibonacci sequence, where we're just starting with 1, 1, 1, and then we keep adding. Add 1 and 1, we get 2, add 2 and 1, we get 3, 3 and 2, we get 5, and so on and so on and so on. Now, because we're using 11 limit tuning, because we're only using these numbers 2, 3, 5, 7, and 11, we have to drop out these black numbers here because they're made of higher primes, 13, 34, twice 17, so on and so on. And that leaves us with a reduced number of usable fractions to define the golden section. These would all be able to be used within metrology, within the ancient measure system, as values here. And there's something very peculiar about these values, particularly phi squared. Now, phi squared is what happens when you add 1, to phi. It's this amazing number that it's 1 over phi. Oh, sorry, I've put 1 over phi squared there. That's a mistake. When you add 1 to phi, it becomes 2.618. When you take 1, it becomes 0.618. It's this very mysterious number. It only behaves like that. And we know that the ancients were completely took up with this because there's evidence for it all over the ancient world. So we've got this 6 to 5. Now, amazingly, if pi was 6, phi squared would be 5. And we've got these, we're seeing these relationships across the ancient measure system. That's my last 15, is it? Okay. So we're going to zoom now. We've got yards to steps, fathoms to paces, and we see here these cubic relationships. And again, they're defined by these relationships between 6 and 5. But here we see the ancient pies. Now these pies start with 22 over 7, and that's varied to 63 over 20, and this other one, 864,275. There are a few other pies, but they're always using those same fractions to nudge it into place. And you see here how those pies are actually defined by these phi squared, these natural principles of number, and they're being used in the ancient measure system to make or to see that out of phi squared emerges pi. As Schwaller puts it, out of becoming, which he calls addition, then comes multiplication, which he calls growth. And pi is a multiplicative function. It makes a flat plane. A circle creates a plane. A leaf that grows is a plane. That's Schwaller's argument, at least. And so we see that by comparing these phi squared values, we're getting these microfractions. Again, by looking at powers of 12, by looking at 6 to 5, we're getting some of the ancient measures. We've got the Roman cubit, the Royal Egyptian cubit, the Hebrew sacred cubit, and here we've got the number of miles in Earth's circumference. And this is the geometry. It's a very simple diagram. It looks slightly complicated here, but it's very easy to draw, and from that single foot we can generate all of the measures. Interesting, up here we're generating a whole another set, which also 528, that's that foot we were talking about of the English mile. 760.32, that's 3/4 of a foot that we're going to look at in a sec. So ancient measure rationalizes geometry, and it wants to preserve the whole numbers in the designs of its temples. I'm going to skip through these and then back. So here we've got pi. Now if pi is rationalized as those values we just looked at, then instead of our circumference being a fractured number, loads of these decimal points going off into the distance, then it's actually, we can just relate them simply as 1 and 3. Here we've got 1 English foot as diameter, 3 Persian feet as circumference, or 8 English feet as diameter, 25 English feet, or 24 common Greek feet. Or here, a circumference of 360 feet with 100 Royal Egyptian feet in its circumference, in its diameter. So the same thing is being done with squares. If we have a foot dimension for the side of our square, this irrational number square root of 2 is rationalized. They're choosing a fractional value for it, and so that diagonal becomes a cubit. Here's a Samian cubit, Belgic cubit, and so on and so on. So this was a very practical method. And what we're seeing is that part of these differences in pi don't only come from phi squared. As I was saying, there's so many ways into this subject, but we're seeing that same difference that's generated between different values of phi squared actually determining the shape of the Earth, because the Earth is a bit squashed. So that means that as we go between lengths of latitude up the Earth, that those lengths increase a little bit. And so the difference, and they reduce back at the pole. So the difference between the mean radius, the average of all the degrees, and the polar radius is this fraction that we've found in phi squared. And here's how all the key latitude lengths in metrology work. I'll skip that because we're running out of time, but I would point you towards John Neal's work for further details. So let's think about a circle. We know a circle is divided into 360. We know that each of those degrees is divided into 60 minutes, and each of those minutes divided into 60 seconds. And we can see there we've got 21600 minutes in a circle and 12,96000 seconds in a circle. And so if we take the model of the ancient world, the model of the world from the ancient world, then we can see that this is the Earth's circumference, 24883.2 miles, or 12 to the 5 divided by 10. And when we get this number here, 12,960 seconds, and we divide 24883.2 by 1296 to get the size of a second, we see a second is this number, 101.376. Now with metrology, we're not looking for fractured numbers, we're not looking for pieces of number, we're looking for whole numbers. And so when we want to understand a length, we don't go to the site and project our measure onto it, whether that's the meter or the megalithic yard or whatever we're working with. We've not got a single fixed standard, we've got a musical scale. And so we're looking for the note. And to find that note, we're looking for the biggest whole number near it. So it's clearly 101 is 100 feet of something. And this is 100 feet of the foot of the mean degree. If we use a different pi on this mean circumference, we get a radius of 3960, which we're all familiar, hopefully, with John Michell's drawing of the moon and the earth and the pyramid. And 3960 is the radius of this big blue circle, the radius of the earth, according to the New Jerusalem diagram. So let's look at metrology in practice. Now, the Great Pyramid must be the greatest metrological object on Earth, and if not the greatest man-made object ever. Now here we've got at the top, there's a picture of the casing stones, the casing sockets that are on the corners, slightly larger than the pyramid. And what do we find? We find that the difference between the base of the pyramid, 756 feet, and the base and the casing stone dimension is slightly wider by another one of these fractions. I didn't explain how we came to this fraction because we've not necessarily got time for that today. But this precision, and we know it's precise because these sockets, we saw the size of them here, not very big, these two lads are sitting inside them, but it's nearly a seventh of a mile, it was just over a seventh of a mile between these two sockets on the corners of the pyramid. And yet the difference is less than half an inch in the height. And that is, some severe accuracy. It's obviously something they really took care of. And here, just very few small facts about the Great Pyramid. Again, I'd refer you to John's work for pages and pages of mind-blowing information. So the base exceeds the mile by this same fraction. We saw that fraction was the mean degree of latitude and the polar degree of latitude were differing by that much. And this is very interesting. If we times the base, the perimeter, 756 times 4, 3024, by 43200, and again, nudge it with that fraction, we get this same mean circumference. The pyramid has been built according to this whole system of thinking. Let's look at the other great marvel, the two big ones here. Now, Stonehenge, these lintels at the top, this is what has been measured and understood as these measures are very well accepted. Everyone's looked at them. John Neal refers to them as the most measured object in the UK. And this is John Michell's drawing of the Sarsen ring. Robin Heath's drawing of the station stone rectangle. So what I wanted to do was to see if I could use that same star-cut diagram to construct these musical intervals between them. So we start with the square of 100 English feet. And then just with simple lines, we're just adding a couple of lines to get these blue dots, and that redefines our distance as a Roman foot. which we know 100 Roman feet is the inner dimension of Stonehenge. Add a few more lines, a few more dots, we get the common Greek foot, which is the outer. And again, we can do the same to expand that into the width of the station stone rectangle. And we're left with being able to actually draw Stonehenge very simply. If you had pegs and strings, you could do this on site as long as you had one reference measure, and it doesn't matter whether you want to start with the station stone and reduce or start with the English foot and expand. It's very easy to do that. Now what's amazing is that this outer diameter of Stonehenge perfectly fits into the polar radius, perfectly fits into the distance between the centre of the Earth and the pole, and it fits 200,000 times. But look, this same distance, this is the pyramid of Quetzalcoatl, this is Stonehenge, and this is the top step, the stylobate of the Parthenon, and they're all exactly that same size. And so this ancient model is clearly understood worldwide. You know, I've picked a few examples here. Here's an example of a Mayan calendar stone. This is a small one in Yale University. And again, it's using this same foot. It's using this same value for the square root of 2, and it's proportioning its rings using this same star-cut diagram. It's the same wherever you go. This building on the bottom right, this is the altar of heaven, a temple in the center of China, the geodetic center of China. It's been rebuilt, but it goes back to about 2,500 BC. And again, it's using the same principles. This building is built in the Royal Egyptian cubit. This is the layout of Jerusalem from John Michell's book. Jerusalem is designed and built in the Royal Egyptian cubit. Howard Crowhurst, who I'm sure many of you are familiar with, he's finding these measures the same at Karnak, which means that they're at least 8,000 years old, although they could have been ancient when they were built. And at the same time, Howard's finding the same principles of the division of the square. And so here we've got this ancient measure system being used practically on the ground to calculate 8,000 years ago. You know, we've got these Neolithic Kong tubes from China. A conservative estimate is about 3,500 BC, but they'd been mining jade since 6,000, so it's very hard to tell exactly how old these are. But look at the level of precision on this. Look at this is made of jade, a hard material to work with, and someone has taken infinite care to get all those divisions right. And John Neal's found the measure system again within these Kong tubes. So what we're really talking about is a measure system that has done a lot. The Earth, we can see from John Neal's work, the Earth was surveyed over 8,000 years ago. The measures around the world, from China to Peru to Neolithic Britain to Egypt, Jerusalem, wherever you go, wherever they've used measure, they're using this measure system. It's been proven in John Neal's work by existing monuments and artifacts, non-controversial information. It's been corroborated by the statements of ancient writers such as Pliny and Herodotus. It can be predicted with mathematics, and you can easily use it in the field with simple geometry. And ancient measure is based on harmonic thinking. It's based on seeing the measure system as an image of the divine. They've chosen to make a system of understanding the world which is based on a model. The model is the divine, or the creation of the universe, the harmonic principle that's torn itself into being. And the standard, because measure is always based on a model, a way of seeing the world, and a standard that we're comparing to, and the standard is something that won't change. If you want a standard, you've got to pick something that you're going to be able to go back to over and over again. The polar radius, the mean radius. These aren't going to change in the lifetime of a culture. They're essentially permanent. And so we've got this way of integrating geometry, music, number, astronomy into this harmonic way of thinking, and it's an incredibly useful tool, and I'd really recommend you go out and buy John Neal's books. researchers have got this tool now that they can apply to any decent survey of any site in the world. And not only is it a tool for researchers, but it's a tool for composition. Artists, architects can use it to tune their buildings, designs, to the actual vibration of the cosmos. Because everything made with this system is tuned to the Earth. And anything that we can measure can be measured with this system. And look, I've applied this same harmonic division diagram. It doesn't matter if it's in a square or it's in a rectangle, it's the same proportions are applied to each side. But you see this scallop shell here, how the harmonics are all the way across. Now, just because the ancient measure systems just using the numbers 1, 2, 3, 5, 7 and 11 doesn't mean nature's going to stick to that. It could be using harmonics all the way up to the thousands. And we see all these lines here that are developing out. Nature itself is expressing itself harmonically. Over and over again, this harmonic way of perceiving the world. And interestingly, Plato was very close-lipped about harmonics. He made a few sort of cryptic references, but he didn't want to give the whole secret away. Gurdjieff the same. He embedded all of these intervals, or many of these intervals, in his long Beelzebub's Tales books, which I don't know if anyone's read. I know I couldn't get to the end of it. And he called it the law of vibration. So what we're looking at here is a whole system of thinking contained within the ruler. We're looking at measure tuned to the Earth, tuned to the qualities of the universe, and we're looking at it at a very, very ancient date. Mathematicians are using the same thing. This on the left is the decay of quantum states in the collider, and it's using the same principles. This is again a numerical representation of that star-cut diagram, and this is again a fractal based on that same numerical relationship. So, what's going on? Is it that the entire universe is a harmonic vibration? This is a standing wave in water. Is it that the universe itself is a standing wave? Is consciousness a standing wave? Are we living inside a vibratory system? Well, I would agree that we would, and I think Plato would agree too, although he might say it's a likely story. And I'll end with this quote from Hermann Hesse. It's the study of harmony in which the musical study of harmony is incorporated, but only as a part. The whole does not apply to human music, but to the music of the universe, the concert of creation. And that's him talking about Kepler, who, as we know, was a harmonicist. Thank you.